In this video, I want to provide a solution to problem number 30 on page 100 of the textbook. The question is simply to find all the values of x where this function is continuous. So when I'm looking at this function, I only see two values of x that are interesting to look at. X equals minus 2 and x equals 2. Because those get defined by themselves, and also this expression for every other value of x is very easy to evaluate and very easy to take a limit at. Because it's a rational function, I would just get to plug in. Another way to say that is, where this expression is 0, well, at minus 2 and 2, those are the only places where this function, this expression in that part, would be discontinuous. So, I want to see what happens at x equals 2, and then at x equals minus 2, using the continuity test. The first part of the continuity test is, hey, does your function exist at the particular x you're looking at? And where ours does. When x equals 2, y is 3. The next part is, does the limit as x approaches 2 exist? All right, well, we need to look at our function and figure that out. We're taking the limit as x approaches 2 of f of x, and we have to figure out if this exists. Can I evaluate this until I get a real number? Well, this part of the function is for where x is equal to 2. For all other values, I'm supposed to use this. And that's the special thing about limits. When x is getting really, really close to 2, the only value I don't care about at all is, well, 2. I'm getting really, really close to 2 without actually ever getting there. So this limit, as x approaches 2, really only cares about this top part. All right, well, now I have two polynomials I have to factor. The bottom is the difference of squares, and the top is the difference of two cubes. And that has a nice formula that you might not have used for a while, so feel free to pause the video and use the internet to pull up that formula just to give yourself a reminder. And now I will use the formula for the difference of two cubes. Now I can cancel out the part that's giving me trouble. I no longer have a 0 on the bottom of this expression. Now I have a polynomial over a polynomial as x approaches 2. It doesn't give me a 0 on the bottom, so I can just plug in that value. So let's see, 2 squared is 4, plus 4 more plus 4 is a total of 12. Divided by 2 and 2 make 4 is 3. So the limit exists and is equal to 3, and the third part of my continuity test is also true. 3 does in fact equal 3. My function is continuous at x equals 2. So I'm going to make a little note of that here. My function is continuous at 2. I want to go through the same process for x equals minus 2. Check my function value. Well, I'm going to get 4. I passed the first part of the continuity test. And now I have to take a limit as x approaches minus 2. All right. Well, I'm going to be sneaky here. Instead of 2, I'm taking a limit as x approaches minus 2. Because all my arithmetic still works just fine. If I was doing this on paper, I'd rewrite it, but I'm using a board, so this is nice. So everything is really the same. It's now I just need to evaluate this limit as x approaches minus 2. And wait, there's still a 0 on the bottom. I would get a number on top, but a 0 on the bottom. So now I need to think about what that means. I have nothing to cancel that out with. If I try to factor the top, I won't be able to using real numbers. And that might be something interesting for you to try. So again, you could pause the video and make sure I'm not lying to you. But what I want to think now is just about the function x squared plus 2x plus 4 all over x plus 2. Nothing to cancel off the bottom with, so if I was treating that like a rational function, because it is a rational function, I would have a vertical asymptote at minus 2. And we could plug in values, but it means my function is either going up or down on either side. And so what I know now is this limit doesn't exist because it is either infinite, it's either going to infinity or minus infinity. This is an infinite discontinuity. So at x equals minus 2, my function is not continuous. All right, so I tested the only two interesting places. For all other values of x, my function is continuous. So down here, I'll give you my final answer, where my function is continuous. Well, it's continuous from minus infinity all the way up to minus 2, but I have to kick minus 2 out, and then it's continuous on the interval after that as well. All right, the exclamation points aren't necessary, but there's my solution to problem number 30 off of page 100.